Hi everyone, my name is Dankrad Feist. I'm a researcher at the Ethereum Foundation, and I'm going to speak about applications of VDFs. It's more than just lotteries, as you will see in this talk. To start, quick repetition about verifiable delay functions. I really like this illustration by Justin Drake. Basically, what does verifiable delay function mean? It's a function, so you have an input and a unique output. You want it to be a delay function, so there's actually another input that sets the difficulty, that it essentially determines how long it will take to compute this function. And it's verifiable, which means it also produces a proof that the result was computed correctly, and this proof is much faster to verify than it takes to compute the original function. Right. So one of the, of course, most talked about applications of VDFs is to use them as a source of randomness. So to go over this, basically, in the real world, if a group of people wants to generate some randomness, what they can do is they all come together, go into a room, roll some dice, and then they do something with the result. Like, say, take the sum of all of the rolls modulo 6 or something. And okay, but the problem with that is, if they do that, maybe one of them will look at the other people's dice beforehand, and they will modify how they throw their die, and then they can cheat and change the result. So we modify this protocol by making it in a dark room, so they can't see the other one's dice, and then at some point we turn the light on, but now it's too late to change the roll of dice, and then then we have randomness where maybe they could have tried to cheat rolling their dice, but they wouldn't be able to know how they would influence the result. And basically, when we use VDFs for randomness, we should think of them transporting this primitive of turning on the light into the digital world of blockchains. Basically, VDFs stop people from turning the light on early. And so this is what we do in Ethereum 2.0, where we need this good, reliable source of randomness in the blockchain, basically to make proof of stake work, but also to make sharding work, where we have the rundown, which is this commit reveal scheme, and we use the output of that scheme for the VDF. And after that, basically, we have some buffer because, maybe it's not immediately included on chain, but then you can use this as randomness, use this to select the next proposers, and you know that you have a reliable scheme to get randomness going forever. Now, to talk more about other possible applications of this, we have to introduce this concept of the so-called AMAX. So when we talk about VDFs, basically we always think, oh, it's this primitive that gives us a certain time, time delay before which it can't be evaluated. Well, how do we know what that time actually is? So what we do is we pour a lot of money into ASIC development and think now we have the fastest possible ASIC. But of course that's not true. If someone is willing to invest a ton of money into developing a faster one, we almost certainly know there will be some acceleration possible. And basically AMAX is our best guess of what is the best thing that, given the best technology in the world right now, could be possible to achieve the acceleration that could be possible. Right. And so basically, when I started thinking about applications more, at the start, we think of VDFs being a cryptographic primitive, right? So it's this, the kind of things that we know as hash functions, digital signatures, and zero-knowledge proofs, that basically they're designed to hold even versus the strongest possible adversaries. We design these things with such strong security margins that we think not even like a huge governmental organization like the NSA would be able to actually break them. And then on the other side here, we have so-called crypto-economic property primitives, such as proof of work, proof of stake, other things that are more recent, like token-curated registries and so on, for which we know actually, like, they don't have these guarantees. They are not cryptographically safe. They're only crypto-economically safe. So they could actually be broken if someone is willing to put a ton of money into it, into breaking those. And these are kind of like a newer primitive that's kind of different. And like when we think about VDFs, we actually might have to change our way of thinking, because if we set the AMAX that we're willing to tolerate high enough, then they work like a cryptographic primitive. Like if we set it to 100 and we develop a really good ASIC, it's very, very unlikely that someone will be able to develop something faster than that. However, once we go more into the direction of lower AMAX, which some applications need, they basically rely on nobody being able to compute it much faster than the ASIC. Then we go more into the range of crypto-economic primitives. Okay, so the next application I want to talk about is preventing so-called long-range attacks. So proof of stake has this problem that's called weak subjectivity. So, you know, in proof of work, you can always find the valid change just from knowing the genesis block and following the chain that has the most work done on it. So this property does not hold anymore in general in proof of stake, because you validators can swap in and out, and once 1/3 of the validators have changed or exited, these validators are actually not bound economically anymore. And so now they can go back and say, well, my private key is not worth anything, so I can just sign some message in the past, it's not going to hurt me. And if enough these have accumulated, they can go back into the past and say, oh, at this point we're 2/3 majority, so we can just start a new chain there. We have nothing to lose because we don't have any stake in this system as it currently exists anymore. Now, the interesting thing is that VDFs, actually even in the way we're going to employ them in Ethereum 2.0, are going to mitigate this problem somewhat. Because if they thought about doing this, here, like when they've all exited, now when they want to build a new chain, that chain is going to miss something. It's going to miss all the VDF work that's gone into the other chain. And rebuilding that will take a very, very long time. And so basically you can see that you can compute that, like the extension of the weak subjectivity period is related to the AMAX in this way. So like basically you need this bit of extra time, like instead of being able to start an attack immediately when you have some majority in the past, you first have to catch up with the current chain on the VDF work. Note that this is only true if you only start the attack like post hoc. If you, from the beginning, you wanted to attack it, you could start at that point and start immediately building your VDF chain. So then this mitigation would not work. Okay, so another application that's is quite interesting, and it's also like one of the projects in the VDF Alliance, is the proof of space by Chia. So Chia wants to build a cryptocurrency based on a Nakamoto type consensus, so like without registration, but they want to build it on the amount of hard disk space that you have on your computer. And so the way they do that is that they have developed this proof of space by which you can prove that you have a certain amount of hard disk space, because they basically have a computation where you need to store huge tables, and if you haven't stored them, then like it would be a huge amount of computation to recreate that. Now, to space those proof of space, they will need a VDF in between. So like basically whenever someone has found a good proof of space, they will need... Sorry, Dankrad. I don't know. Oh, that's a good idea. Sorry, Dankrad. Right. Okay, so basically in between those proofs of space, we need to space the blocks out, and they have basically this concept of two different kinds of participants in the network. Ones are the farmers; those are basically the ones investing the work, and in between you have time lords who run a VDF that guarantees the spacing between the blocks. And the spacing that they provide, those time lords, is basically computed from the hash of the previous proof of space. And that basically means that if someone has a really good proof of space, which is equivalent to a very low block hash, then that would be picked up by the time lord because they can compute the VDF quicker. And basically, if they hadn't got this protection in between, then you could grind. Like if you even have a small amount of space, you could just like change your input and tweak it until you get a good proof on your next selection, and you could potentially very quickly, given them enough computation power, you could build a different chain that's longer than the original chain. A somewhat similar idea is behind Filecoin. In this case, it's called proof of spacetime. And what they want to build is a network that actually stores useful data. So instead of like this proof of space, they have a proof of replication that actually shows that you store some data that can actually be useful in this case. Then in order to create the proof of spacetime, what you do is you run this in sequence with a VDF. And each VDF output will fiat Shamir the next proof of replication, so that the aggregate of all of these shows that you have stored a file or a number of replications of a file even over a certain amount of time. So in the end, you would probably run like zero-knowledge proof, like a snark type of argument on this to like aggregate this into a very short proof that you have stored this file. Right. Here's one interesting idea on running auctions. So, like when you have auctions, like you have this problem that people want to get their bids in at the very last moment because it's better for them not to reveal what the actual value of something is. And so they always wait until the very last possible moment to get their bid in and basically snipe it away from the other participants in the auction. So one kind of old concept to prevent this were so-called candle auctions that work by having like a candle burning in the room where the auction is going on, and when that candle has burned out, the auction ends. And so it's hard to know when exactly it stops, so that changes like the dominant strategy in the auction, so that you want to get your bid in early, because otherwise you risk just not getting anything at all. And basically the VDF here replaces the candle. So the VDF itself, the output of the VDF would be used to say when the bid period stops. So you have a fixed bid period, and then retroactively you take a cutoff, actually this is when it stopped. And since nobody knows when it is, you better get your bid in the beginning. Another interesting idea is like, if you want to prevent front running in decentralized exchanges, this is by the injective protocol, the idea. So here's the problem. So you have this decentralized exchange, you have like a make order that's put in at this block H0, and then someone wants to make a trade. And this trade might be like a large trade or something that tells someone else, like an attacker, that, oh, actually I should like buy this first because the price is going to rise. So they put in a competing order, and yeah, basically like since it's on a blockchain, like as long as it hasn't been included on in a block, it's not determined which one would go first, and in Ethereum, probably the one that bids more gas would get it first, and so the front runner could just ensure that he would be the first one to include their order, which is kind of unsatisfactory. So here is one neat idea on how to remedy this. Basically, as soon as you know you want to put in your order, you start running a VDF, and you regularly update the order with the current output of your VDF. And basically, the contract accepts whichever order has more VDF work done on it. And that basically, well, I mean, if the VDF is somewhat tight at least, that would ensure that the original order would get in, whereas the other one would not take precedence. Right, here's another neat idea that is about zero-knowledge proofs. So basically we can design zero-knowledge proofs that can expire. So we basically can build in the property that we want the zero-knowledge proof to show that we have like done a certain computation, but we only want that proof to be valid for a certain amount of time. And the way we could do that is by designing a zero-knowledge proof that alternatively accepts the witness or a correct VDF output. And when I give you a proof, there's no way for you to tell which of the two I have. So that means that after this sort of VDF time has expired, it's possible for anyone to just have the proof, and it doesn't actually prove anything anymore. Time lock puzzles are another sort of application that isn't actually directly based on the verifiable delay function primitive, but both are based, like basically the most sort of, most of the currently used VDF primitives also work very well for time lock puzzles. And the hardware that is going to be built for VDF is actually going to be usable for time lock puzzles exactly as it is. And so that's also one possible application, which we can use for a different flavor of expiring zero-knowledge proofs. In this case, let's say we want a zero-knowledge proof where instead we want that it's not the soundness that expires as previously, but it is the zero-knowledge property that expires. So after a while, the witness that you have put into the zero-knowledge proof actually gets revealed. And how can you do that? So here instead, you have one input that is the witness, and then you prove to the proof that you give it also a correct time-locked witness. And then basically you have to, that would be a public input, and then anyone could later like lock that, solve that time-lock puzzle, and then they would have the correct solution to that witness. Yeah, so as a summary, like there's like a very active field in finding those applications for verifiable delay functions. We've seen quite a few here. What basically is right now kind of the problem is that we have those like very like applications that mostly rely on like relatively relaxed AMAX assumptions like randomness, candle auctions, which is also actually, when you look at it, very closely related to the randomness property. And then many of the others, the applications are going more in the crypto-economic direction. So like weak subjectivity mitigation, yes, you can do it on like even on a large AMAX, but it would not have a very big effect. It would only be 10% if it's an AMAX of 10, say. And similar for all the others, like if you have a high AMAX, then those properties are not so interesting. So basically, what we need now is like to make it a good crypto-economic primitive. It would be great if we had better incentives around it, because right now this is what nobody has fully figured out. How do we make sure that the best VDFs actually will be developed in public and like everyone will have access to them, rather than them only being developed by someone who wants to attack a system. And in order to do that, we need some continuous incentivization in the protocol for faster VDFs. Yeah, and yeah, the main difficulty with that is that it's kind of a winner takes it all primitive. Like usually it's only the fastest one who wins anything, whereas like with other proof of work type primitives, you can, like everyone gets rewarded proportional to to their speed. Yeah, thank you. We have time for questions.
I think we will have a discussion.
Okay.
Later.